Okay, let's start lecture 14. Another application of differentiation, which is least squares here. What is least squares? Okay, that's the method of getting approximation. Let's get started with it. Okay, typical engineering problems. There are lots of engineering problems which can be stated in this manner. You have a theory on a set of data, naturally, and want to find if the theory explains the data. Okay, well, that's data first, then theory kind of things. Or you have a major data set and want to build a mathematical model to it, and you don't know what kind of theories are applicable, but you'd like to find out a mathematical model, which is an equation for that. Okay? But how? How? Well, answer is minimize the difference between the data and theory or a model you're going to come up with. Naturally, that's reasonable, but how do we define the difference here? Okay, that's the catch. If we can define a difference which does make sense, then we are on the right track. So let's start. And that error is called the root mean square error, RMS error. Okay. All right, so let's assume that we have a data set here in pairs. For each value of x, we have measured the value y. So you have a set of x and y, or capital N of them. And the model you have here, where alpha and beta are parameters, you can adjust. All right? So if we have this set, then RMS, root mean squared error, is defined as the value minus the model value equation, what the equation tells you, and take the difference, and difference squared, and 1 over n, which is actually the average squared error, and take the square root. So root mean squared error. Okay. So what's here? Let's go. Wants to minimize this error with respect to alpha and beta, of course. If we can minimize this error with respect to alpha and beta, that should be the model you will come up with. For that, what we do, minimizing it. Aha, yes, the differentiation is what we are going to use. Okay, but not so fast. Think before start computing. This is very good. How should I say? The way of thinking for the engineers, because if you are going to minimize this, you are going to differentiate it. So if this equation is easy to differentiate, that's nice, right? So what we do is this. Okay, minimizing e is the same as minimizing the squared here, right? If square is minimized, itself is also minimized, because this thing is always positive, cannot go to negative, right? So if that is positive, then that is always the case. So therefore, instead of minimizing this error here directly, we minimize this thing called the j, which is just the squared error summed up. 1 over n is gone because that is just a number, so we don't have to worry about it. Okay, so we are going to minimize this quantity here. So okay, we are going to use the star notation. That's what the value you are going to get, the best value for the parameters. Using those best value parameters, you can compute the RMS error, the best error, the smallest error. Okay. Then J star is can be written as J alpha star beta star, which is this one here. Okay, so that is minimizing J alpha beta in terms of alpha and beta. That means this one here. So therefore, what we do, I'm repeating myself again, differentiating. But there are two parameters. So therefore, we are going to differentiate partially. Partial differentiation with respect to alpha and beta. And set both of them equal to 0. You have 2 equations and 2 unknowns. So you should be able to solve. All right. So differentiating in terms of alpha and beta, you get those equations. Okay. The difference here is that you have computed the squared, so 2 comes out, and this thing here, and inside you differentiate in terms of alpha. That's chain rule, right? So that's what you got. This is minus sign delta alpha of f. Same thing here, beta. So you got those 2 equations and set those 2 equations to be 0. Right. Let's see. Well, up to that equation, everything is general. Okay, nothing is assumed about the function form of f and so forth. But if we assume linearity in terms of parameters, we can go forward and we can get more solid results. So let's assume that the model equation f is linear in parameters. And for that, let me use a simplest example here. This is a model. So that's, this thing here is fx alpha beta. So this thing is linear in terms of alpha and beta. Okay. Because what you do is linear combination only. So this is what you got. Then what you can do is you can compute those partial derivatives using those equations. Sorry about that. Let me get rid of this here. Okay. All right. So differentiating this one here, y, and minus this one here, and that's easy, right? This you get xn, this you b, you get here 1. That's all you get. So therefore, this is what we got, xn multiplied to 3 of them, 1 multiplied, you have exactly the same thing. And minus is sitting here, so this plus minus is changed, minus is sitting here, that's. And of course, what we do is to set that thing equal to 0, but before that, let me do a trick, small trick. Well, this thing here says that you take the difference and then sum them up. But since this is a linear thing, this summation is also linear, so you can distribute, right? Linear combination. So therefore, this entire thing is sum of this, sum of that, sum of this, and linear combination of those. That's what you got. In other words, you can sum each term separately. Okay. Here, probably one thing I should mention is that this thing here. So you have summation of b. And if you take b out of summation, because b has nothing to do with the summation, then the rest, what's left is 1. So you are adding 1 here. Okay. So setting those 2 equal to 0, we get those equations. You had 2, you can just get rid of that, and you can move this term to the other side, and this is what we got. Well, I got rid of those. We know that small n changes from 1 to capital N, so let's forget about that. Mathematicians are lazy, okay? So I'm lazy, so let me forget about that. Okay then, what we do? We write those equations in vector matrix form, as we have done many times. So this is the form which has lots of beautiful symmetries and so forth. And this equation has a name, which is normal equation. That's the name of this equation. Okay. So unique solution for this normal equation exists, and which is inverse of this matrix here multiplied to this constant vector here, right? And here D, if you remember the inverse matrix, D is a determinant, right, of this matrix. So therefore, D is a determinant. And if that is not equal to 0, then you can use this one here. So D is determinant of this that's given by this. It's not equal to 0. Okay? So you have a solution here. If this is not equal to 0. Then most of the time, this is not equal to 0, so you have a solution. Okay? Note that, well, this one I already told you that 1 is the only thing which is left. And you're adding 1 n of them, so that has to be n. Easy. Okay, so A and B, if I write everything down, 1 over D, and this times that, this times that, and that. Let me call this 1 over D A and B, A and B's. Let me compute A and B separately. Okay? Well, for that, I guess it is easier if we have numerical example. So therefore, I'm going to talk about this example here. Data points x at -1, 0, 1, 2, and 3. We measured certain thing. I don't know what it is, but let me call that y. That's 7.35, blah, blah, blah. And this is what you got. All right? So this is the data set you have. Okay? Find the model. Once again, y is equal to x plus b. So data sets are plotted at those points. So what we want is to find a dotted line, that one here. It's not like this one or not like that one. The one which has the smallest squared error. Okay? That's the one that you want to have. Oop. All right. So for that, expand the table to compute components of normal equations. Remember that xn squared, summation of x squared, and other things appeared. Okay, so let's do that. So that's the original part. The model is this one here. So those are used. X times y was in it, and x squared was in it. Okay, and those three, bottom three, let's discuss that later. This part. This has to do with the model equation, and those are errors. And those are the ones we are going to use. Summation of x, y, and x times y, and x squared. All right. So D is x squared summation times n minus xn summation squared. So that's 15 times 5, n of them, 5 of them. And that's summation of x is equal to 5, that's 5 squared. So you can compute that. 5 times 5, 75 minus 25 is equal to 50. Okay, how about A? A was n times this minus this times that. 5 times 82, 85 minus 5 times 58, 87. That's about 121.4. And B is negative of this times that, and this square times y. So that's negative 5 times this and this. And that's 464. Oh, that's a large number. Okay, so now you have A, B's, and D's in that equation, so you can compute A, which is A over D, which is this one, that, 2.43 here. And B is 9.29 here. So those values. So this is B star, and this is A star. Okay. So now we have A stars and B stars. You have model equation, therefore you can compute this one here. Okay. So using the model, we have this. And if you have y, you can take the difference between y and m and compute the error. And you can square that and add them together. And for the sake of comparison, I added en itself. En could be positive or negative, right? As you can see, this is positive, negative, whatever it does. And if I add them together, this is 1.8 times e to the minus 15. Very small number. Okay. sum of errors is very small number. And sum of squared errors, this one here, we have 1.730. Is that good or bad? Well, let's compute from this one here, the RMS, root mean squared error, which EAB, which is equal to 1 over square root of, square root of 1 over J over N, right? So that's over 5.59. So compared to that, what I do is this. About 5% of average YN value. YN summation was 58.57 divided by 5 is 11.7. So that's the average Y. Average Y. And compared to that, 0.59 is such a small number. Only 5%. Right? So if this experiment was performed by my student, I would say not bad for a student. Okay? It's a good number. Okay? So it is always worthwhile to check the EMS error, RMS error. Here. All right. Coffee break. So pretty much that's all you need to do. Normal equations. The compute the elements which are needed for the normal equation and plug into the normal equation to get the values. Meaning of D, determinant. This square times summation of 1, which is actually the number of data. And that. So what does this mean? This is xn squared. And if I do change that into this form, that's more understandable. I guess that this is another one of those do nothing mathematical trick, right? I multiplied n squared and divide by n squared. Okay. Well, what we had is this one here. If you divide this one was by n squared, you have 1n here, so you only have 1 over n left. Here, next one, divided by n squared, you have square here, so you can put n within this. So what does it say? This is nothing about the average of xn squared, right? There are n of them, so average of xn squared. This one here is, the inside is average of x. So average of x squared. So that's the difference between average of xn squared and average of xn squared. Okay? Well, n squared times, yes. That's just the weight. And there is a very nice inequality in mathematics, Cauchy-Schwarz inequality. You have heard about that? Probably not. But if you have heard about that, that's going to be great. This says that the summation of something squared times summation of something other thing squared is greater than equal to the summation of the product of those squared. And equality holds here. Equality holds only when one is a scalar multiple of the other. Okay? So, if I use inequality with un is equal to xn, okay, here, and vn is equal to 1, then this becomes, this one here is greater than or equal to vn, un, xn. This equation is what we got. And therefore, this minus that is equal to d times n squared. No, divided by n squared, whatever. N squared is just a number. So this is greater than or equal to 0. Aha, equality when? When d is equal to 0 is a point which we don't want to have. Equality when xn is equal to k, constant. Because the other one is constant, right? Those two could be scalar multiple of the other only if xn is just a number. Xn is equal to k, constant. So what do we mean by that? All data are on a vertical line. Okay, so what we have here is x, here's y, 0, here is xk or xn, or well, not xn, I'm sorry. I should have written this as k. And all the xn's are that. Okay. So this is one line which cannot be expressed in terms of ax plus b. Can you express this as ax equals to b? No way. So when the line, any of those lines you can express using this one x plus b, but this is not. So this is the only one which cannot be described by that. Therefore, the assumption that we use ax plus b as a model fails. Okay, no longer valid. So that's why it doesn't work. Okay? But as you can see, it doesn't happen in a real situation, right? X is the value you can choose, and you don't vary x and making lots of experiments. No way. You vary x and see how it changes. So this doesn't happen in the real situation. Okay. From that, it's a little bit different, but there is always a question asked. I was not sure whether this is the right spot for this coffee break or not, but let me anyway discuss this. No differentiations and integrations in computers. So we have learned a lot about differentiations and integrations, and well, computers cannot do that. We can do it. Computers cannot do it. Why is that? Both requires a limit of delta something is equal to z, to 0. Delta z, well, in the differentiations, delta x, whatever sitting at the bottom. And the integration, once again, the whatever that's sitting here, delta t or delta x, whatever it is. Something has to go to 0. In other words, we are taking limits. And obviously, we cannot do that because time flows discretely in computers. In computer, time doesn't flow continuously. How does it flow? Do you know the concept of clock pulse? Clock pulse. In a computer, we do have a thing called the clock pulse, and the status of the computer circuitry, digital circuitry, changes only at the clock pulse. Okay? Nothing can change in between. Say, for example, 10 gigahertz machine. One clock pulse every 1 over 10 to the 10th second. Tiny, tiny bitty. Okay? Well, in other words, what it tells you is that the minimum delta t is this clock pulse. And nothing can change, meaning that the delta t cannot be smaller than this one. This is the least smallest value you can get. So, delta t goes to 0? Ha ha. Obviously not. All right. Fact 2, numbers are discrete in computers. Wow, time is discrete and numbers are discrete. Yeah. Pi, say for example, does not exist within a computer. Concept of word length. You know word length? Where your machine must be a 32-bit or 64-bit machines. So what do you mean by that 64-bit? Okay. Well, I use the old one, 32-bit numbers, meaning that the dynamic range of 2 to the 32. 32-bit, each one of them represents one digit of binary number. So there are 32 of those. So the maximum number is the 2 to the 32. So that's, well, dynamic range is that. The smallest number versus largest number, what's the ratio? That's dynamic range, 2 to the 32. Okay, so the minimum you can get is the whatever the maximum number times 2 to the minus 32. 2 to the minus 32, right? And it cannot get any smaller than that. So the delta x goes to 0. No way, you can't do that. So value-wise or time-wise, you cannot take the limit. So therefore, you cannot have differentiations and integrations in the computers. So what they do, what can we do within the computer? The only thing we can do is, instead of integration, summation. Instead of differentiation, you take difference. That's all we can do. Okay, that's the end of this lecture.